Hello students, today's topic is imperfection in solids. So how imperfections can get into solids when they are getting cooled down, and during that time their atoms or molecules are getting arranged, and in doing so they have some imperfections sometimes, as in this case we have arranged a disk of certain atoms. This is showing the arrangement of atoms in a solid. And now let's see what could be the imperfection. So we have voids. These are spaces in between these atoms, voids. Now these cannot be filled. And now what happens when these solids are getting cooled down? Sometimes it may happen that some of these atoms may move somewhere else out of the atom structure, or maybe a crystal, or out of within the same crystal somewhere else, or some other type of atom may take place, or there may be change in the line of arrangement within the crystal. So what are imperfections? Any irregularity in the pattern of crystal arrangement in a solid lattice is called imperfection in solids. The occurrence of defects takes place when crystallization occurs at a very fast or at an intermediate speed. This is because particles do not get enough time to arrange themselves in regular pattern. Okay? Now we will be studying about point defects that can be classified into three types: stoichiometric defects, impurity defects, and non-stoichiometric defects. So what are stoichiometric defects? These are the point defects that do not disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamic effects. Basically, these are of two types: vacancy defects and interstitial defects. Now let's know about these defects. So vacancy defect is when some of the lattice sites are vacant. This is vacant. Okay. This results in decrease in density of the substance because the number of particles present here are less than it should have been. So this reduces the density of the substance. This defect can also develop when a substance is heated. How? Consider this atom. This whole crystal is getting energy, so they are getting energy, and then whenever any of the atom acquires sufficient amount of energy, it can happen that it might jump after excitation. So it could occur like this also. Now next is interstitial defect. Here we have picture of a perfect crystal. It should be like this. The arrangement of atoms or molecules we are also calling constituent particles. And if any other type of particle comes and arranges between these spaces, then this is interstitial atom or point defect. Now what is going to happen? The whole density of the crystal will change because there are more number of particles in the given space than the normal situation. Vacancy and interstitial defects can be shown by non-ionic solids. Ionic solids must always maintain electrical neutrality. Now these are non-ionic. There are no charges, there are no repulsion, no any other type of interaction in this case. But if they are charged, the situation will be described some other way around. So rather than simple vacancy or interstitial defects, they show these defects as Frankel and Schottky defects. Now, in this picture, we are going to talk about Frankel defect. Frankel defect is a type of point defect in crystalline solids named after its discoverer Jakob Frankel. The defect forms when an atom or smaller ion, usually cation, after losing electron, cations uh, are having smaller size than their parent atom. So cation leaves its place in the lattice. In this lattice, this is a lattice formed between sodium and chloride ion. Now in this position there should be sodium, but because of this change it has moved to somewhere else into this point. Here it is. So leaves its place in lattice, creating a vacancy. Here is the vacancy and becomes an interstitial by lodging in a nearby location. It creates a vacancy defect at its new location. It does not change the density. Is there any change? No. The number of particles are same, though it has moved to somewhere else, but it is within the crystal, so the density has not changed. Frankel defect is shown by ionic substances in which there is a large difference in the size. So we have sodium ion comparatively smaller than chloride ions. They are larger in size, chloride ions. So this arrangement is seen, this defect is seen in such ions having charge or size differences. Now this is Schottky defect. It is basically a vacancy defect in ionic solids. Once again, in order to maintain electrical neutrality, the number of missing cations and anions are equal. So we have again sodium ions and chloride ions. They are forming a crystal in which two places are vacant. One is previously it was occupied by chloride ion. It has to be here. And this was occupied by sodium ion. It is not there. But electrical neutrality is maintained because equal number of both the ions are absent. So there is no effect on electrical neutrality in this type of defect. Like simple vacancy defect, Schottky defect also decreases the density of the substance. That is clear because few ions, or maybe we can call atoms or molecules, has left the place within the crystal, so there will be decrease in density. This diagram represents the impurity defect in which foreign atoms replace some of the atoms making up solid or that squeeze into the interstices. Now in this case, what is happening? We have cation vacancy. That cation could have one positive charge. Now an impurity has gained the position, interstitial position, cation with extra positive charge, 2 positive. All the cations are having one positive charge, but this cation has 2 positive charge. So it is maintaining electrical neutrality of the crystal. These defects in ionic crystals arise due to the presence of some impurity ions at the lattice sites or at the vacant interstitial sites. For example, if molten NaCl, if we take example of NaCl, Na will be acquiring all the A positive sites, and some other impurity like strontium chloride is used, then strontium Sr will acquire this position and will be having Sr2 positive charge. Here sodium could have been placed, but now it is not there. This Sr2 positive is providing electrical neutrality. So some of the sites of sodium ions are occupied by Sr2 positive ions. For such Sr2 positive ion introduced two sodium ions, Na positive ions, are removed to maintain electrical neutrality. One of these lattice sites is occupied by strontium ion and the other remains vacant. Therefore, these vacancies result in electrical conductivity of the solid. Okay, students, we have seen stoichiometric defects and impurity defects. Now it's time to learn about non-stoichiometric defects. These defects discussed so far do not disturb the stoichiometry of the crystalline substance. This is what we have seen. However, a large number of non-stoichiometric inorganic solids are known which contain the constituent elements in non-stoichiometric ratio due to defects in their crystal structures. These defects are of two types: metal excess defect and metal deficiency defect. So let's begin with metal excess defect. We have this picture. So what happens? A metal excess defect arises due to anionic vacancies. When crystals of NaCl are heated in atmosphere of sodium vapor, the sodium atoms are deposited on the surface of crystal. The chloride ions diffuse into the crystals of the surface of the crystal and combine with sodium atoms to give NaCl. So those vapors has formed NaCl with the crystals within the crystal. Now what happens? This happens by loss of electron by sodium atoms to form Na positive ion. We all know sodium is very easy. It's easy for sodium to lose electron, so it loses, and this electron is here. This happens by loss of electron. Now this released electron diffuses into the crystal and occupy an ionic site. This site should have been occupied by any anion, but now an electron is there which got diffused into the crystal. As a result, the crystal now has an excess of sodium because other anion is not there. Chloride ion is comparatively less in number, sodium ions are more. The anionic sites occupied by unpaired electrons are called F centers. Here F stands for German word Farbencenter, meaning color center, as they impart yellow color to the crystal of NaCl. In metal deficiency defect, there are many solids which are difficult to prepare in the stoichiometric composition and contain less amount of the metal as compared to the stoichiometric proportion. In some cases, the positive ions may be missing from the lattice sites. For example, here, the extra negative charge may be balanced by some nearby metal ion acquiring two positive charges, or maybe it should be having more ionic charge than the other ion. In this case, this is A positive, 1 positive, then it should have A2 positive. If it is A2 positive, then it should have been more than 2 positive, that is 3 positive or 4 positive, as this situation is shown by those ions or those elements or atoms which are having which show various oxidation states, like in case of iron, ferrous oxide and ferric oxide and many other such elements. So the extra negative charge may be balanced by some nearby metal ion acquiring two positive charges instead of one. This type of defect is possible in metals, okay, having various. Now we have I have already used this diagram. I'm using once again in this context. Let's take an example of iron. If Fe2 positive is there, then this type another type of cation here could have been Fe3 positive. So what happens is electrical neutrality is maintained, though the stoichiometry is not the same. It's not the same, as these are two different oxidation states. Now students, let's come to the next topic, electrical conductivity of solids. We all know solids conduct electricity because of electrons. Though in molten state, these solids conduct electricity in ionic form. They have ions to conduct electricity when they are in molten state. So, solids can be classified into three types on the basis of their conductivities. First is conductors. The solids which with conductivities ranging between 10 raised to power 4 to 10 raised to power 7 per ohm per meter are called conductors, and metals have conductivities in the order of 10 raised to power 7 per ohm per meter are good conductors. And then insulators, they are far away. These are the solids with very low conductivities ranging between 10 raised to power minus 20 to 10 raised to power minus 10 per ohm per meter. And in between conductors and insulators, there are semiconductors. These are the solids with conductivities in the intermediate range from 10 raised to power minus 6 to 10 raised to power 4 per ohm per meter. So let's see how conduction takes place. We have this diagram. In this diagram, we have valence band and conduction band for insulators, semiconductor and conductor, which are drawn against their energy level. So let's see valence and conduction band. These are two different energy levels separated by a certain amount of energy. We have electrons in valence band, and until and unless these electrons are moved into conduction band, there is no conduction of electric current. So this gap is very large in case of insulators. The main difference between the valence band and conduction band is that valence band specifies the energy level of electrons present in the valence shell of an atomic structure. Means they are, when they are in their valence shell, then only these electrons are available. Until unless they jump to this conduction band, there is no conduction of electric current takes place. Larger the gap, lesser the chances of conduction. So in case of insulators, this is very huge, this is not so big, the chances are more of conduction, and in case of conductors, they are almost overlapped. In case of semiconductors, this is special case. The gap between the valence band and conduction band is small. This is shown here. Therefore, some electrons may jump into the conduction band and show some conductivity. Electrical conductivity of semiconductors increase with rise in temperature, since more electrons can jump to the conduction band, because we all know that heat energy will increase the kinetic energy of those electrons, and it will be very easier for them to jump this small gap. So next, substances like silicon and germanium show this type of behavior and are called intrinsic semiconductors. The conductivity of these intrinsic semiconductors is too low to be of practical use. Their conductivity is increased by adding an appropriate amount of suitable impurity, which is added to this valence band. This process is called doping. Doping can be done with an impurity which is electron rich or electron deficient. That means having extra electrons or less electrons as compared to the intrinsic semiconductor silicon or germanium. Such impurities introduce electronic defects in them depending upon the availability of number of electrons. Okay, let's understand why they are doping those elements. First, we will consider silicon. Silicon, symbol Si. Atomic number of silicon is how much? 14. So electronic configuration 2, 8, 4. Whereas in case of phosphorus, let's see atomic number. What is the atomic number? 15. Electronic configuration 2, 8, 5. And in case of boron, if it is added as impurity or doped into the crystal, its atomic number is 5, and then electronic configuration 2, 3. This is how we are using those values. Silicon has 4 electrons in its outermost shell, whereas phosphorus has 5. If into the crystal of silicon this phosphorus is added, means silicon is removed and phosphorus is put into its place, then there will be 5 electrons, and amongst those 5, 4 will be utilized to make bond with neighboring silicon. Consider this silicon, this phosphorus, silicon, silicon, and this silicon around it. There will be 4 electrons shared by this phosphorus, and the fifth electron will be somewhere else, but that extra electron will be responsible for the increased conductivity. Now let's see another case. If silicon crystal is doped with boron, boron has 3 electrons in its outermost shell, so silicon has 4 electrons. Now it is doped with boron. This is boron's electron, and how many it has? It has only 3 electrons. That will be given or shared. We are having only one here, not showing all the big structure that will be shown in a figure later on. But now this silicon electron, this another. Now boron is forming or using its 3 electrons. Consider these 3 to be electrons contributed by boron. Now there is vacancy. This is hole, which will be helping in conduction. How? Let's see the diagram. So we have this diagram to explain the behavior. One is electron rich impurities forming n-type semiconductor, another is electron deficient impurities doped forming p-type semiconductor. So how they are forming, let's know about n-type. This is normally a silicon crystal would look, in which all the silicon are having or sharing their 4 electrons surrounding 2 other silicon atoms. Now in case of n-type of semiconductor, what we have done, we have doped the crystal with phosphorus. It has 5 electrons, so it will be sharing 1 electron to each silicon around it, but the extra electron will be somewhere else. Maybe it could be represented over here, anywhere, but that will be responsible for conduction. That will help the movement of electric current. Now let's see another case. We have doped this crystal of silicon with boron. We have B having plus 3 electrons, so there will be less number of electron, so there is a formation of hole with one of the neighboring silicon, and that will be behaving as positive charge carrier, and conduction will take place. So let's see electron rich impurities. This is case with silicon as well as germanium. They have 4 electrons in their valence shell. Their crystals are formed with neighboring 4 similar atoms. When doped with group 15 element like phosphorus or any other which contain 5 valence electron, they occupy some of the lattice sites. This is what we have seen, and this forms n-type semiconductor. And in case any other type of electron deficient impurity is added, this type of semiconductor forms, which is p-type. This is also called electron deficient, and this is electron rich impurity. So various combinations of n-type and p-type semiconductors are used for making electronic components. You must have heard about diode. Diode is a combination of n-type and p-type semiconductors and is used as a rectifier. Transistors are made by sandwiching a layer of one type of semiconductor between two layers of the other type of semiconductors, and for example NPN, in which P is sandwiched between N type of semiconductors, whereas PNP type of transistor is made when N type of semiconductor is sandwiched between P type of layers. And these transistors are used to detect or amplify audio or radio signals. The solar cell is an efficient photodiode used for conversion of light energy into electrical energy, and we have already seen LEDs, light emitting diodes, which are also semiconductors. Okay students, let's proceed to our next topic about magnetic properties of solids. Now, before going to that topic, let's recall what we have learned about electrons in class 11th, about the spin quantum number. It tells about the spin of the electron. So we all know that electrons are represented like this in an orbital, and here one is moving clockwise and another is anti-clockwise on its axis. They are rotating, and this means they are charged particles, and if they are rotating or moving on their axis, they can be influenced by external magnetic or electric field. So this is how this magnetic field is related with their presence, their rotation. So let's see what we know. Each electron in an atom behaves like a tiny magnet. Its magnetic moment originates from two types of motion. Its orbital motion, which is in which it is moving around the nucleus. This is orbital motion, nucleus, and electron is moving around it. This is one type of motion, and the other type of motion is when it spins on its own axis. Electron, being a charged particle and undergoing these motions, can be considered. Okay, what they can be considered? That they can be having magnetic moment. Thus, each electron has a permanent spin and orbital magnetic moment associated with it. That means if external field is applied, they will be influenced by that magnetic field. So on the basis of their magnetic properties, substances can be classified into 5 categories: paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. And before going to that point, let's understand what is going to happen if one electron is moving clockwise and another is anti-clockwise. Those electron spins can be represented by this value, and if one is influenced by magnetic field, then the other one is also influenced by magnetic field, but in another way. That means they are cancelling the effect of each other if they are paired, and if they are not paired, in that case those unpaired electrons are influenced similarly. I mean, if they are attracted, then they will be attracted towards the magnetic field. And if they are getting repelled, then that in that case nobody is counter those repulsions. So we have this picture for paramagnetic substance. They are weakly attracted by a magnetic field. They are magnetized in a magnetic field in the same direction. They lose their magnetism in the absence of magnetic field, and paramagnetism is due to presence of one or more unpaired electrons which are attracted by the magnetic field. This is what we all know here in this diagram. We have these small domains in a crystal which are haphazardly arranged in the absence of magnetic field. Now if there is some external magnetic field, in the presence of that field they will be arranged like this. When exposed to an external magnetic field, internal induced magnetic fields form in these materials that are ordered in the same direction as the applied field. Once the applied field is removed, the materials lose their magnetism as thermal motion randomizes the electron spin orientations. And then how paramagnetism works? It results from the presence of least one unpaired electron spin in materials, atoms, or molecules. In other words, any material that possesses atoms with incompletely filled atomic orbitals is paramagnetic. The spin of the unpaired electrons gives the magnetic dipole moment. Basically, each unpaired electron acts as a tiny magnet within the material. When an external magnetic field is applied, the spin of electrons aligns with the field. Because all the unpaired electrons align the same way, the material is attracted to the field, and when the external field is removed, the spins return to their randomized positions. Now, diamagnetism. Diamagnetic substances are weakly repelled by a magnetic field. They are weakly magnetized in a magnetic field in opposite direction. Diamagnetism is shown by those substances in which all the electrons are paired and there are no unpaired electrons. Pairing of electrons cancel each other, their magnetic moments, and they lose their magnetic character. So H2 and NaCl are some examples of such substances. Here we have diamagnetic material in external magnetic field, and this is what happens to the field lines. They are getting repelled, they are getting far away from the material. This is because they have all electrons paired. Now let's see ferromagnetism. Let's take an example by using a diagram. This is a piece of iron. Consider this to be piece of iron in which there are these small arrow-like structures. These are called domains. They are not aligned to a single direction. They have different directions. They are arranged to different and therefore they are cancelling the magnetic moment of each other. Now if they are placed within the magnetic field, what happens? They will be experiencing this change in the direction of their domains. They will point towards the external magnetic field together, and their magnetic moment will add up. They will start attracting toward the external magnetic field very forcefully. This will take place in the presence of external field and the external field can also magnetize these substances. So a few substances like iron, cobalt, nickel and are attracted very strongly by a magnetic field. and these substances are called ferromagnetic substances. Besides strong attractions, these substances can be permanently magnetized. In solid state, the metal ions of ferromagnetic substances are grouped together into small regions called domains. These regions, okay? Thus, each domain acts as a tiny magnet. We have seen these are tiny magnets. So, in an unmagnetized piece of ferromagnetic substance, these domains are pointing or oriented toward and haphazardly any whatever direction they may be. But in case of influence of external magnetic field, they are directed towards the field. So, this increases the magnetic effect. So now this diagram represents antiferromagnetism. It is a type of magnetism in which solids such as manganese oxide, in which adjacent ions that behave as tiny magnets spontaneously align themselves at relatively low temperatures into opposite or anti-parallel arrangements. Look, this is pointing towards upside, then this is downward, and its neighboring is also downward. So they are they are uh, getting affected by magnetic field, but they are cancelling the overall effect. So what happens? The magnetism from magnetic atoms or ions oriented in one direction is cancelled out by the set of magnetic atoms or ions that are aligned in reverse direction. This occurs in antiferromagnetism. This diagram represents ferrimagnetism. It's a type of permanent magnetism that occurs in solids in which the magnetic fields associated with individual atoms spontaneously align themselves some parallel or in same direction as in ferromagnetism, and others generally anti-parallel or paired off in opposite directions. So we have these arrangements, but the main point of observation is their sizes. They are not of equal size, so there will be cancellation but not effective cancellation of the effect. The effect will be diluted. The magnetic behavior of single crystals of ferrimagnetic materials may be attributed to the parallel alignment. The diluting effect of those atoms in antiparallel arrangement keeps the magnetic field of these materials generally less than that of purely ferromagnetic solids, such as metallic iron. Iron, in that case, they all are aligned towards the one direction. They all are influenced by same magnitude or size of the domain. But here, these are not aligned into one direction, and they are not having same size. So the influence is not so great. The overall effect is they are not so much influenced by the external magnetic field.